All right, now, so far I've only showed you basically the principle of how things work with some pretty pictures, but I want to take it a step further and show you a concrete application of how these signals actually work from a mathematical perspective. Because so far it only looks like magic, and just this little detail, extra detail, I think could be useful. If you ever want to know the details. I apologize. This is probably the most mathy part of this entire lecture. So what I'm going to show you is I'm going to show you how the RSA asymmetric key cipher works. This is it was invented by Rivers, Shamia, and Alderman, three professors from MIT. It's quite widely used. For instance, use it whenever you use online banking. But it's not something that actually, to be very honest, not used in blockchains directly. They use something called elliptic curve algorithms. Those are similar, but it's just that RSA algorithms are slightly easier to explain. So this is why I go with that. Right, so before I can do that, I have to talk a little bit about the background math and specifically some features of number theory. So number theory is essentially the part of math that looks at how numbers interact, and there's some cool things if you are kind of interested in these things, such as prime numbers is the simplest things. These are numbers that have only two divisors, which is one of themselves. So as a first step, I want to define something referred to as when one number A is prime relative to another number. So let's say 4 and 5. 4 is prime to 5. Now 4 is not a prime number because it has 2 as a divisor, other than 1 and itself. But it is prime relative to B because together their greatest common divisor is 1. Now, there is, from this concept, there is a famous function which is called Euler's phi function. That is basically for any number n, the number of natural numbers that are prime relative to that number n. It has interesting properties. In particular, when you have two numbers, a number which is a prime number, then Euler's phi function is that number minus 1. And in particular, if you take the product of two prime numbers and then compute what their phi number is, it is simply the product of the few phi functions. So if you take, say, 5 and 3, two prime numbers, then the phi function of that would be 5 minus 1 multiplied by, so the product of what is 5 and 3 is 15. So the phi function would then be 5 minus 1, which is 4, and 3 minus 1, which is 2, and the product of those numbers is 8. So here's a few examples. You have the numbers 1, 5, 10, 12, 14, and 15, and you see the corresponding phi numbers. So as I said, for 15, the phi number is 8, and you can basically go from there. All right, now one thing that will come up, and this is going to get really a little tricky, but there's a task that will come up when we define the RSA algorithm, and that goes as follows. Suppose you have a number n. Then you compute for that number the phi function, and then you pick a small number, e, that is prime relative to phi of n. Now, once you have that, what you're trying to find is a number d such that if you multiply your e with d, and subtract 1, and then divide that result by the phi function, you receive as an output an integer. Or put differently, they are basically phi is a divisor of d times e minus 1. Or if you take d times e and you do it modulo, so that basically look at what remains if you do the division, then that remainder is 1. How do you actually get such a number? It looks a little tricky, but it's actually quite simple. Suppose e is a small number. What you're looking for is then a number k, such that if you multiply k with n and add 1 to it, and divide it by e, then you get an integer number. So I'll show you all of this with an example and how it applies to the RSA algorithm in just a second. So how do the RSA component work? So first you start with two prime numbers because they will be very convenient in our computation. Let's start with P and Q. P be 53, for example. This is just an example. And Q could be 59. Then you compute the product of the two. So that's 3,127. For 3,127, you compute the phi number. Now that's easy because this n was the product of two prime numbers, so it is just the product of the two phi functions, which is the number itself minus 1. So in this case, that's 3,016. This is an important number, this n, keep this in mind. Then what we're going to do is we're going to select a small number e that is prime to phi of n. So for instance, if you have 3016, so what you're looking for is that is a number which does not, where n cannot be divided by that number. So for instance, for 3016, the smallest such number that we can find is 3. Okay. All right, and then what we do, and this is where we're going to find this number k, so that we can compute what's referred to as the multiplicative inverse. So if you take your phi is 3016, and we take a number 2, then if you multiply 2 with 3016 and add 1 and divide it by 3, then you get an integer number. This integer number is one that we're interested in. In this case, it's 2011. So now what we'd want to do is we take all of these numbers as they work together, and they have some special properties that we're going to discuss in a second. So, all right, let's just look at this. Now, what we want to create is we want to create a private key and we want to create a public key. The private key for this combination of numbers is the combination of the number n, 3027, and the special number d that we picked ourselves. Likewise, the public key is the number 3 that we picked and the number n. So you can publish these two numbers. These are the latter two, and then you can use that to decrypt messages or to encrypt messages, depending on the problem that we're trying to solve. So if you think that this is all a little too much, let me show you how the math works out in the next example, where we're trying to encrypt a message. So the message that we're going to pick is, in this case, is a number 89. Okay, so we want to send a message 89. Alice wants to send that to Bob without somebody else being able to see it. Now, what Alice is doing is she wants to encrypt the message. How is she doing it? Well, she takes this number 89, raises it to the power 3. This is the number E. This is the public key that Bob has posted. And then she applies the modulo function using this n. So she takes 83 to the power 3, modulo 3127. That's the number 1394. You can always find these numbers. There's no problems with that. So this number C, this number 1394, that's the cipher. So what she now does is she sends the cipher and she sends this cipher to Bob. And anybody who is looking will not be able to determine that C, so 1394 is the cipher, the encrypted version of 89. But Bob can use his private key now and decrypt it. How? Well, what he does is he essentially takes the cipher and raises it to the power of the private key, which was 2011, puts in the modulo operation of using n, and voila, he gets the message 89, using the private and public keys that we discussed before. So as you can see, this is the beauty of it, this math works out. You can do it for yourself, pick any other message as a numerical number and perform these operations, and you will get the same outcome. Now, the next application I want to show you, and this is the one that we're actually aiming for, and that's the application of RSA, this algorithm to using digital signatures. So what we're going to do here is, again, we choose our P's and Q's as before. We compute our phis of n function and so on and so forth. We choose our E and we pick our D. And then we have the public keys and the private keys as before. Now, the message that we want to sign, not send, but sign, is 89. So what we want to do is we want to create a digest which proves that we indeed sent that message. So how do you do this? Well, the signature is produced as follows. I take my private key and take the message and raise it to the power of the private key and perform the modulo operation. And that gives me an output of 545. That number is my signature. And then how do I validate it? So Alice sends that information to Bob. How does Bob check that this is indeed the outcome, the proper signature? Well, he takes the signature, raises it to the power of the little number E that we picked, performs the modulo operation, and gets as an output, indeed, the message. So, and since the message corresponds to the message that he has also received from Alice, we know that it's a valid message. So now the last thing we need to do is we need to put this all together. So hashing is widely used, provides a convenient output of fixed length, and therefore is a concise representation of information. So that's useful. I hope you agree to that. Public-private key signatures ensure that you can prove ownership so that nobody can misappropriate your funds, and you have a certain level of security that way. So this cryptography is very useful. Now, just to be clear, in blockchains, encrypting messages is a lesser concern because the information that you provide for transactions is actually supposed to be out there in the open. Now, but you may ask the question as follows. You see, well, M, the message that I gave you was just a number. We were really looking at text. So how does this all fit together? There seems to be still that I'm just using some abstract math for no particular reason. Well, the next step is actually a very simple one, and that goes as follows. What we have created is hashes. Hashes have a fixed length. So we take any arbitrary text and have a fixed length output that we can then deal with. Now, one of the things which you may or may not know is that you can actually take any text and you can convert it to ASCII code. So the convenient part about it is we take a long text, create a hash, which is a fixed length. That fixed length is then converted from you running using ASCII code into a number, and then we can apply all of the signature math from the RSA algorithm that I showed you, so far, and produce the right signatures and the right outputs. And that is the beauty of it. So all of these pieces together give me exactly a workable combination of factors that we can then use for the blockchain and put on the blockchain.